This is the second of 3 lectures from Chapter 17 about thermodynamics. And the first lecture was really an introduction to thermodynamics and the concepts of enthalpy and entropy. In this second lecture, we're going to talk more details about enthalpy and entropy, how they fit together to determine something called free energy. And so this was the very last slide from lecture 1. So just kind of refresh your memory. We left it off with that there are 2 factors that determine whether or not a reaction is spontaneous, and that is the enthalpy or heat of reaction, and the fact of whether it's exothermic or endothermic, and of course enthalpy change is delta H, and the second factor is entropy change, delta S, which you can think of as freedom of movement. And those delta S and delta H work together to give us a property that we call free energy, represented by delta G. And we'll be doing some calculations in this lecture. I'm going to talk, first of all, a little bit more detail about enthalpy and entropy individually before I put them together. This is really from an earlier chapter in 1211. It was an introduction to thermochemistry. So this should really kind of be a review. So you may not find this specifically in chapter 17, but I think it's chapter 5 that it's from if you want to review from your text. But again, change in enthalpy for our purposes, we can think of that as heat of reaction. It's not always the same thing as heat, but under our conditions, which is constant pressure, it's okay to think of them as equivalent to one another. So let's look at a reaction, for example. Let's say we were burning natural gas or methane, and the products of complete combustion are always carbon dioxide and water. So if you were to look at this diagram, enthalpy is a form of energy, as is entropy. So if we have enthalpy increasing along the y-axis here, you can see that the reactants of this combustion reaction are at a higher energy than the products. Okay, so what does that mean? That means as we go from reactants to products, energy is given off, okay, or heat is given off. What type of reaction do we call that? We say that it is exothermic. And just kind of a little nugget of information to store in your memory cells. Combustion reactions are always exothermic. That's why we use them to heat our homes and warm us and all sorts of things. But they're always exothermic. They are always exothermic. And if you remember the sign convention for enthalpy, that means that the change in enthalpy for the combustion reaction will always have a negative sign in front of it. So remember these 2 nuggets. If you're taking notes or writing down key things to get out of a lecture, this is a reminder about exothermic and endothermic. The delta H always has a negative sign if it's exothermic, which is energetically favorable, and a positive sign if it's endothermic, and that is not energetically favorable. This slide is pretty redundant. It just is a cool example. I don't know if many of you have seen this, but if you generate hydrogen gas, in this case, it's inside the balloon. And if oxygen is also present and you give it some little spark, like for the activation energy to get it going, you will get a nice little explosion, and the product of that is water. So that's just another example of an exothermic reaction. There are tables of what we call standard enthalpies of formation. So delta H for enthalpy. If you see a little F as a subscript next to delta H, that is indicating it's enthalpy of formation. Now, it is important to understand this definition. We will be using enthalpies of formation, and it'll probably be something like a multiple choice question. So the definition for enthalpy of formation is the amount of heat required to form 1 mole of a substance from its elements, okay? So here's kind of the generic equation, But if I asked you to write an equation that represented the heat of formation for water, look back at this definition and let's see what we would be doing. Okay, well, first of all, if it's heat of formation, it has to be forming 1 mole of the product, so this has to be a 1. What are the elements that make up water? We have hydrogen and we have oxygen. The other part of the definition is that all the materials, all the elements must be in their standard state. That means how they exist naturally on our Earth. How does hydrogen exist naturally on our Earth? As a diatomic element. Same with oxygen. We have a problem now, though. This reaction isn't balanced, and I cannot change this 1 because the definition of enthalpy of formation is that we form 1 mole. So the only way to balance this is to use fractional coefficients in front of these diatomic elements. So I need 2 hydrogens, so I'm okay with that. Oxygen I only need 1 of, so I have to put a 1/2 to balance the equation in front of the molecular oxygen. So this would be the equation that represents the heat of formation for water. Okay, so you may want to write that down. That's an important piece of information. What these heat of formation values or tables are most commonly used for is to calculate the heat of formation for a chemical reaction. So I will put reaction as a subscript here. So if I had a reaction, let's go back to burning natural gas. And I asked you to calculate the enthalpy of this reaction. I'm going to abbreviate reaction RXN. That's what chemists do. If I ask you to calculate the heat of reaction for this combustion reaction, there. One way to do it would be to look at a table of heats of formation. They're usually like in the appendix of your book on a test. It might be a page of that has a table in it. And you would need the heat of formation for all of your reactants and all of your products. So you'd need it for methane, you'd need it for molecular oxygen, you'd need it for carbon dioxide, and you'd need it for water. So you would get the values given in the table, and you would plug them into this formula shown at the top of the page, okay? Where the heat of reaction, enthalpy of reaction, equals the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. Where this little N and M are the coefficients for the balanced reaction. So you would have to put a 2 in front of the heat of formation for oxygen, 2 in front of the heat of formation value for water. So let's look through an example doing that. Here's another combustion reaction. If you have 3 carbons, the prefix for that is prop. So this is propane. That's what you have on your grills outside. So combustion of propane, and this is a balanced reaction, okay? And plugging into our enthalpy of reaction, of course you have to account for the coefficients. So remember, it is products, the sum of a heat of formation of products minus the sum of heat of formation of reactants. So products come first, right? We have 3 carbon dioxide, so we have to do 3 times heat of formation of carbon dioxide, which you would get out of a table. It happens to be minus 393.5 kilojoules. Make really sure that you have the signs correct here. Again, it's the sum of the heat of formation of all of the products. So, of course, water is another product. There are 4 waters in the balanced equation. Here's the heat of formation for water. Put brackets around. Once you have all the products summed up, make sure you put brackets so you don't mess up your sign. And then it's minus heat of formation of all of the reactants. So you have 1 propane. Okay, so there's that, heat of formation of propane. and you have, check this out, this is an important feature. You have 5 oxygen. Oxygen is an element. This is really important. Listen, listen, listen. The heat of formation for all elements in their standard state is 0. Okay? That'll help you out. So molecular oxygen is 5 times 0. You don't even have to show it. You see an element and you just leave it out. Now you're ready to do the summation. And this is easy peasy, except I can't tell you how many people mess up the sign, mainly because they don't put brackets around the products and separate them from the reactants. All right, so let's talk about entropy for a bit. You can do the same type of calculation for entropy. There are tables that have entropies of reaction. And just like we could do with enthalpy, and in the future you'll see we can also do with free energy, we can sum the enthalpy of the products minus the sum of the enthalpy of the reactants, and that will give us the enthalpy of a reaction. Okay, so this is very, very important right here. Enthalpy is never 0. Actually, the third law of thermodynamics says that, I don't mean enthalpy and entropy, says the entropy of a crystalline material at 0 Kelvin is 0. Of course, we can never reach 0 Kelvin, so we can never prove that. That value is extrapolated from experimentation. But the bottom line is, for your purposes, under standard conditions, you will never ever see an entropy value that is 0. That would mean all motion has ceased, which is never the case. Remember, just a reminder, different from enthalpy and free energy, entropy is favorable, energetically favorable, when it has a positive sign, okay, when it's increasing. Let's do an example for entropy. I want to point out something. I'm thinking of all the errors, the pitfalls that students fall into. Look at the units for entropy. You probably didn't even pay attention to units for enthalpy. You may have. But enthalpy values are almost always given in kilojoules. Entropy, on the other hand, because the values are quite a bit smaller, are almost always given in simply joules, not kilojoules. So down the line, in a few slides, we're going to be wanting to combine enthalpy values with entropy values. Guess what? You can't do that until you match units. Okay? It doesn't really matter if you change the enthalpy units to just joules or if you change the entropy units to kilojoules. But make sure the units match before you try to add them together. All right, so you do this entropy of reaction the same way we did enthalpy. Products minus reactants, no surprises. All right, onward to free energy. This is really the whole point of Chapter 17. Free energy, represented by G, named after the scientist that worked with it, Gibbs, so it really stands for Gibbs free energy, is really important because what is Gibbs free energy? It is the energy available to do work. Okay, as we've talked about before, the amount of energy in our universe is constant. However, not all energy is as useful as other energy. If energy is too diluted or already too used or dispersed, we can't use it to do much for our purposes. So delta G is energy that's available to us to do work, useful energy. And it also predicts whether or not a process or a reaction will be spontaneous. So here's the holy grail of thermodynamics reaction right here. That's an equation you will be using an awful lot. You need to commit to memory and understand it. It says that free energy, the amount of energy available to do work, equals the change in enthalpy for a process minus temperature in absolute Kelvin times the change in entropy. So as you can see, the free energy for reaction is dependent on both enthalpy and entropy and temperature. Delta G has a mathematical sign of negative for a spontaneous reaction. So it's energetically favorable if it has a negative sign. If it happens to have a positive sign, if delta G has a positive sign, that process is non-spontaneous. Oopsie. Okay. Let's look at an energy profile for a chemical reaction. So let's look at the production. This is the Haber process. I guess the right German way to say it is Haber, but I've always said Haber. Of ammonia from its elements, nitrogen and hydrogen. And notice along the y-axis, we have free energy, or delta G, or I should just say G. Yeah. And along the x-axis is reaction process, reaction progress. Okay. And so on the left side, we think pure reactants. Okay. And on the right side is pure products. Now, the Haber process is reversible, and it does reach equilibrium at some point. So let's look at the change in free energy as the reaction progresses. In the beginning, delta G decreases. So what does that mean? That means if delta G is decreasing, that means the change in free energy is negative. Okay, right here. Delta G is less than 0. It's negative. Okay? That means it's favorable. So in the beginning, when we combine nitrogen and hydrogen, it's a very favorable reaction. It is spontaneous. It reaches a point right here where it's non-spontaneous, right at the bottom. What happened? Non-spontaneous. Okay, so at the bottom, at this low energy point, there's no more driving force for it to proceed anymore. And what that is, when you reach the bottom of the energy profile, when it's the lowest energy possible, that is equilibrium. And that's what happens in equilibrium. That's why a reaction will progress to a certain point and then say, oh, we're done. We don't want to make any more product because we're at our lowest energy point. That's where we're going to sit here and take a nap and chill out, and we're not doing any more work. And so that's why things like Le Chatelier's principle and other things come in to try to jolt an equilibrium out of the position it's in so that we can make more product. And so if you try to push the reaction beyond this to make more product, so you're going uphill now, what would the change in free energy be for this segment? It would be greater than 0 or positive sign, which is non-spontaneous. Okay? So this uphill part is not going to happen unless you give it energy from the outside. And here's our now familiar equation. So if you are given a table with standard free energy of formations, you can use that information to calculate the standard free energy of a reaction, just like we did with delta H and delta S. Again, any free energy change that is negative means not only that it's energetically favorable, but that it's spontaneous. Remember that G is the only factor that can determine spontaneity. Okay? Delta H and delta S contribute to determining whether a reaction is spontaneous, but neither of these alone can determine spontaneity. Only delta G can. All right, here's where it starts to get tricky. This is going to be kind of a brain drain for you. So if you need to take a little break, come back when you're fresh. But from now on to the end of this lecture, you need to pay very close attention. So I'm going to start out with a question to get you thinking. With this free energy equation in mind, what values of enthalpy and entropy will result in a spontaneous reaction? Okay? So we know that in order to be spontaneous, our free energy must have a negative sign. Okay? So what signs should enthalpy and entropy have so that delta G is negative? Here's a table similar to the one I gave you kind of a brief overview of in class today. But if you have a process or a reaction that is spontaneous all the time, under all conditions, that means that both enthalpy and entropy are favorable always under all conditions. So delta S entropy is favorable when it has a positive sign, when it's a positive change in entropy. Delta H is favorable energetically when it's exothermic and has a negative sign. When you have these two combinations, a reaction or process will be spontaneous under all temperatures, all conditions. So kind of the opposite of that, if you have a process that is non-spontaneous regardless of what temperature you subject it to, so that means that delta G is positive always, the change in free energy is positive, that means that both enthalpy and entropy are unfavorable all the time, which means entropy has a negative value, that's when entropy is unfavorable, and change in enthalpy would have a positive value, would be endothermic. When both of these terms are unfavorable, that means that the free energy will be non-spontaneous under all conditions. All right, here we go. Here we go on to the tricky stuff. What if entropy and enthalpy are fighting one another? What if one of them is favorable and the other one is not? Who wins and what determines it? So let's look at those two scenarios. You could have a situation where enthalpy is favorable, which means it has a negative mathematical sign of negative. That's exothermic, that's energetically favorable. And you might have that in that same situation have entropy that's unfavorable. A change in entropy that's negative would be unfavorable. So which of these wins? It's like a tug of war. One saying, come on, let's be spontaneous, and the other one saying, no, I don't want to be spontaneous. So who wins? It all depends on temperature, okay? In this case, and I'll go over this in a little bit more detail later, in this case, this type of reaction is spontaneous at low temperatures and non-spontaneous at high temperatures, okay? Let's look at the other situation where we can have a conditionally spontaneous reaction. So let's say in this case that entropy is favorable. Okay, we have a positive change in entropy, it's favorable, say, yay, let's go spontaneous. Look over at enthalpy, however, and enthalpy is endothermic, positive sign, which means that is not favorable. Again, which of these wins? Okay, which of these is going to determine that whether or not the reaction is spontaneous and under what conditions? As always, temperature is the determining factor in these iffy situations. And in this type of situation where entropy is the driving force, the reactions are spontaneous only at a high temperature, and they're non-spontaneous at a low temperature. I'm going to explain to you on the next slide why this is, okay? And although just memorizing this information would allow you to answer a multiple choice question or two, if I were to ask you an essay question, for example, to explain what I'm getting ready to tell you, you really truly need to understand it. So again, have a fresh brain and go to the next slide with me and I'll explain this a little better, hopefully. All right, so here we go. Let's look at the first situation where enthalpy is unfavorable. In other words, it's endothermic. And entropy is favorable, okay? Mathematical sign of plus. Which of these terms do we want to dominate if delta G, the free energy, is to be favorable? That is with a negative sign. Which of these do we want to dominate? Clearly, we want the T delta S term to dominate, okay? Because this negative sign is key here. The larger the delta S value is, okay, the more negative, larger term this becomes, okay, and therefore the better chance delta G has of being negative. So we want to minimize the enthalpy term because it's unfavorable, and we want to maximize the entropy term because that's what's favorable. How do we maximize the entropy term? By increasing the temperature, okay? If T goes up, this whole term goes up. So high temperatures will make this type of situation favorable, okay? So let's look at the other situation. The other situation is that delta H enthalpy is actually favorable, has a negative sign. That means exothermic reaction, ready to go spontaneous, right? Except along comes entropy and says, no, I want to be obstinate and be unfavorable. I don't want us to be spontaneous. And so in this case, what do we want to do? We want to minimize the unfavorable segment, which in this case is entropy. Remember, there's a T in front of it. How do we minimize the entropy section? By minimizing temperature, okay? Wherever entropy goes, it's accompanied by temperature. And so that's how you control the importance of the entropy term, is by adjusting temperature. So in this bottom case, we want to reduce temperature, and that will increase the spontaneity. Okay, that makes it spontaneous. In the upper case, where we have endothermic reaction, we want to increase temperature. Okay, let's work an actual example to show you the impact of this. It's actually pretty fascinating, I think. Let's think about melting a piece of ice. Okay, that's all we're doing here, going from solid water to, or solid H2O to liquid H2O. And let's calculate the difference in the free energy as we change temperature. Okay, this is a perfect example because melting ice at room temperature, which is around 25 degrees Celsius, is spontaneous, right? Yeah, no problem. Which would mean at 25 degrees C, you expect delta G, the free energy, to have some negative value because it's spontaneous. But if you change the temperature to 0 degrees, is melting ice spontaneous anymore? No. Okay, it's non-spontaneous at 0 degrees, which means at 0 degrees, delta G must be positive. So let's prove that with some calculations. First of all, let's evaluate the situation. What is the change in enthalpy for this process, going from a solid to a liquid? Okay, I'm hoping that you realize that it is an endothermic process. Anytime you melt anything, you have to apply heat, which means it's endothermic. Okay, so that is, the enthalpy is unfavorable for this process. And the entropy is, I'm hoping you can look at this, entropy when you go from a solid to a liquid is favorable. And when entropy is favorable, it has a positive sign. So now you have a classic situation where you have enthalpy and entropy battling one another. One is favorable and one isn't. Who wins and under what conditions? It all depends on temperature. So let's plug numbers in and see. This problem says calculate the free energy at two different temperatures. Calculate it at 10 degrees Celsius and at minus 10 degrees Celsius. Here are the values for change in entropy and change in enthalpy for that reaction. I was nice to you in this case, and I gave you enthalpy in joules instead of kilojoules. But as I warned you before, most problems won't do that. So first thing you want to do in most problems is make these units match. All right, so here we go. At minus 10 degrees, so you're just going to plug in your values for delta H, which I gave you, okay? Here's temperature. It must be in Kelvin. Okay, so you've got to convert all your Celsius to Kelvin. And here's the value for delta S. Plug and chug. We get free energy of 218. That is a positive value, which means it is not spontaneous. Okay, ice going from solid to a liquid is not spontaneous at negative 10 degrees, which is true, right? That's about the temperature of your freezer, and ice ain't melting in there, so that is non-spontaneous at that condition. However, at positive 10 degrees Celsius, plugging in the same values except for temperature, we get a free energy value of minus 224 joules, which means at this temperature, it is spontaneous, and that is true. You take ice out anytime, anywhere above 0 degrees Celsius, and it will spontaneously melt. So that kind of just gives you quantitative view of how spontaneity can depend on temperature. Do you think I'm warning you enough? You can tell what students do all the time. Again, remember that entropy values are given in joules and enthalpy values are given in kilojoules. You've got to match those units up before you do any calculating. All right, let's do another example. Here is our Haber process again, making ammonia from nitrogen and hydrogen. You were given, we'll just say, table values of heat of formation for the reactants and the products, and entropy of formation for the reactants and products, and you are asked to calculate G. So let's look how we would do that. And I am now noticing I got lazy here and cut and pasted the answer. It's a little fuzzy. I think you can still read it. Okay, so let's look at our handy dandy equation. Delta G is delta H minus T delta S. Okay, so before we can calculate G, we need to calculate delta H and delta S. Remember, since we're talking about a chemical reaction, that what this is asking for is a delta G of reaction, and that comes from the delta H of reaction and the delta S of reaction. Do not get these entropy, free energy, and enthalpy reaction values mixed up with enthalpy of formation and entropy of formation. Okay, so in order to get the enthalpy of reaction, which is what we want for this equation, we're going to use our handy dandy formula where we sum up the heat of formation of products minus the heat of formation of reactants. That's what was given in this table. So heat of formation of products, what is our product? It's ammonia. The balance reaction shows that we make 2 ammonia. The heat of formation value for ammonia is minus 45.9 kilojoules. Yay for heat of formation being 0 for elements. We just leave those out. And so our heat of formation for this reaction is 91.8 kilojoules. Okay, great. We do the same thing with entropy. The entropy of the products. So entropy of ammonia, 193. There are 2 ammonia, 2 times 193. And that is our product. Subtract the sum of the entropy for all of the reactants. Remember, entropy is never 0. You're not going to get lucky like you do with enthalpy. The entropy for molecular nitrogen is 191. There's only 1 of them. And there are 3 hydrogens. Okay, and the entropy for hydrogen is 130.6. When you do this math, you get that the entropy of reaction is minus 197. This is where you need to be careful of units. Enthalpy is kilojoules, entropy is joules. Okay, so again, unless the problem specifies what units they want, doesn't really matter. They just have to match each other. Now that we have the enthalpy and the entropy, we can now plug them in to the free energy equation. All right, so here we go. The enthalpy of reaction that we just calculated is minus 91.8. Make sure you change temperature to Kelvin. And in this case, I converted the minus 197 joules to 0.197 kilojoules. So my units are going to be in kilojoules. When I plug and chug, I get that delta G of this reaction, the Haber process, is minus 33.1 kilojoules. It has a minus sign, which means it is spontaneous. People use the Haber reaction as an example so often. You might as well just memorize that it's spontaneous, and you'll kind of have a way to check yourself if I ask you that. That is it for the second lecture. I think this is the trickiest lecture of the chapter. And so I strongly recommend you begin working as many problems as possible. There is a practice worksheet in the content section.